Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 1.3 from your textbook, which introduced you guys not only to the existence and uniqueness theorem for first-order differential equations, but also to slope fields. In this video, we're mostly going to just be working through a couple more examples of building slope fields and seeing what we can visualize about the solutions to differential equations without actually solving them. But before we do that, we're going to take a look at at least one sort of slightly more complicated slope field, and we sort of need one sort of computational trick that'll help us a little bit with this. This is not a necessary thing when building slope fields, but your book definitely is a big proponent of this, and it can be sort of useful. So I at least wanted to talk a little bit about it and look at one example of it. So we're going to give a quick definition here. An isocline, so an isocline is a curve in a slope field where along every point of the isocline, the solution curves to the corresponding differential equation have the same slope. So in other words, an isocline is basically a curve inside of the slope field where along that curve, the solution curves always have the same slope. In other words, it's basically a way of finding all the places where the solution curves have the same slope. Isoclines, basically, if you guys ever were to study some more advanced things like things called like differential geometry or further courses in differential equations and things like that, isoclines have a lot more importance in them, and you can study them in a lot of different interesting ways. But for us, they basically give us a way to speed up drawing in slopes in slope fields, especially in a situation where both x and y show up in that f of xy expression where we set y prime equal to f of xy. If we don't use isoclines, we have to manually take tons of different combinations of x values and y values, plug those into the differential equation, and use those to figure out the derivative of each point. Isoclines are basically an efficiency technique. So what this basically tells us is, before we get to our first example, is if we can determine the isoclines for a few basic slope values, say maybe like slopes of 1, 2, -1, -2, just slopes that are easy to draw, then we can sketch in those slopes all over the slope field very quickly. So let's go ahead and take a look at an example very similar to the last example we did in the previous video, but making use of this isocline feature. All right, so we've got a new differential equation here. We're going to consider this first-order differential equation, y prime equals x over y. Keep in mind that this differential equation is first order, but non-linear. It's non-linear because that y is in the denominator. That means it's sort of inside the function 1 over something. So there's being a function applied to y, so it is non-linear here. We're going to do a couple things. We're going to prove that every IVP of the form y of x0 equals y0, where y0 is not equal to 0, will have a unique solution. That means that anytime where y is not equal to 0, we will avoid having our solution curves intersect each other. At y equals 0, we won't be able to have any information, so who knows, but everywhere else we know the solution curves won't intersect. Then we'll find all those equilibrium solutions to this differential equation. Remember, equilibrium solutions are basically solutions of the form y equals a constant. And then we're going to sketch the slope field through this differential equation. And then we're just going to, for fun, to make sure we really understand what a slope field is showing, we're going to indicate the solution curve on that slope field that corresponds to the particular IVP y of 2 equals 1. Okay, so let's start with A here. So since we want to try to prove that these IVPs have unique solutions, we want to try to use the existence and uniqueness theorem for first order diffEQs. Okay, so notice that this is already in the format of y prime equals x over y. So our capital F of xy in this case is x over y. Then we need to look at the partial of this with respect to y. So we're taking the partial derivative of this with respect to y. So if you want, you can think about this as x y to the minus 1. Remember, when you're doing a partial derivative here, you're treating the x as a constant and only differentiating that sort of y. So we get negative x y to the negative 2, which would also be negative x over y squared. So there's our function, and there's our partial derivative. What do we notice about both of these? Well, both of these are rational expressions, but of course, as long as that y is not equal to 0, then we know that they're going to be continuous. So fxy and the partial of f with respect to y are both continuous as long as y is not equal to 0. So IVPs of the form y of x0 equals y0 will have unique solutions if y sub 0 is not equal to 0. So as long as we stay away from y being equal to 0, we know that the function and its partial with respect to y are both guaranteed to be continuous. So the existence and uniqueness theorem for first order differential equation assures us that their corresponding IVPs will have unique solutions. What happens near y equals 0? Well, we don't know. Remember, when the conditions for the existence and uniqueness theorem are not satisfied, we get no information. So all we were able to do is say that the IVPs that avoid having an initial condition where y is equal to 0, those are guaranteed to have unique solutions. All right, let's go ahead and talk about the equilibrium solutions. So, equilibrium solutions. Well, for equilibrium solutions, remember these would be the solutions of the form y equals k. So we're going to plug in y equals k into this, and of course if y equals k, then the derivative is going to be 0. So we've got to solve 0 equals x over k. If you attempt to solve that, you get 0 equals x. What does this mean? Does that mean that 0 is an equilibrium solution? No, because this is saying that x needs to be 0. But equilibrium solutions are supposed to be y equals k. So we would need to come up with k values that solve this. So no values of k solve this. So no equilibrium solutions. So notice that we were trying to find equilibrium solutions where y equals k. When we try to solve for k, we don't find any values of k, we find a value of x, but that's not what we're trying to solve for. So there are no values of k that solve this, so there are no equilibrium solutions. So there are no solutions of the form y equals a constant that satisfy our differential equation. All right, let's put all this stuff together and try to draw the slope field here. So we'll give ourselves a new page here. Okay. So for C, let's remember the information we have. IVPs with y of x0 equals y0, y0 not equal to 0, have unique solution. That was from part A. Let's just actually remind ourselves that's from part A, and from part B, no equilibrium solutions. So for C, we want to try to build this slope field. So for the slope field, we've got our axes there, and we'll give ourselves some points. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. Okay. Now, let's think about how we sort of approached the last one. When we did this in the previous video, we first sketched the equilibrium solutions. Well, unfortunately, there are no equilibrium solutions, so we can't put that on there. The next thing we sort of did is we sort of made a table of values. So we said, okay, if we choose different x and y values, then we can determine y prime by using y prime equals x over y, which is the equation of our differential equation. Now, remember, in the previous example, only y featured on the right-hand side. So we only had to pick y values, and then it didn't matter what x was. We just plugged in y values, and that told us everything. But here, every time we switch either x or y, we'll get a different derivative. Now, if you want, you could just try to brute force this. You could say, okay, let me try 1 and 1, and then maybe 1 and 2, and then maybe 1 and 3. And then maybe that's enough ones for x, so maybe I'll do 2 and 1, and then 2 and 2, and then 2 and 3, and just try all these different combinations. But the sort of efficiency technique is to try the Isocline method. So before we try to do this, let's go ahead and make a little, if we want, we can always come back to this and fill this in with extra ones, but let's try this Isocline method. So, Isocline method. Okay. So, let's suppose, right, we're going to look for slopes of, say, value. Now, your book often uses k, but we sort of use that for our equilibrium solutions. So let's say slopes of value m. M is often the letter we use for a slope when we're doing, y equals mx plus b. So why don't we just use that here? So where is it always going to have a slope of m? Well, that means that we'd get something like m equals x over y, which if you think about it then is my equals x. So we get that y is equal to 1 over mx, and that's as long as m is not equal to 0. So what this basically tells us is if we want to find all the places that say have slope 1, we just need to look at where y is equal to 1 over 1x. So we can make a little list of our isoclines. So I'm going to make a little isocline table. So the isoclines, the different slope values, I can pick things like slope of 1, slope of 2, slope of -1, slope of -2. And the isocline that's associated with that is things like y equals x, y equals 1/2 x, y equals -x, y equals -1/2 x. Now you might be saying, okay, how does this help? Well, you guys know how to draw things like y equals x and y equals 1/2 x, y equals -x, y equals -1/2 x, and everything along those lines are going to have these slopes. So let's draw in this. Everywhere that would be along y equals x is going to have slope 1. So let's draw that in. Where do we have places that are along y equals x? So that would be things like 1, 1 is going to have a slope of 1. Things like 2, 2. Things like 3, 3. Things like 4, 4. Things like 0, 0. Things like -1, -1. -2, -2. -3, -3. -4, -4. Now, could I have just manually done that? Sure, if you go back and you try to do your table and you put in 1, 1, you'll find a slope of 1. If you put in 2, 2, you'll find a slope of 1. And so you would find all these one at a time if you did this. But notice, by doing a little bit of work here, I can do those much more quickly. Now let's try this. Anywhere that is along 1/2 x, I should draw a slope of 2. So what are things that are along 1/2 x? Well, we know that that would be like 2, 1. So we should put like a slope of 2 there. And like 4, 2, that would be there. So we'll put a slope of 2. I guess 0, 0. So notice that weird things are happening here at like 0, 0. But that makes sense because we know that bad things happen near y equals 0. There's no guarantee about unique solutions there. -2, 1. So we've got sort of something that looks like that. And then 4, -2. Or -4, -2, excuse me. So there we go. So all those have slope 2. And all those fit along that line of y equals 1/2 x. Okay, let's draw these on. Slopes of -1 all along y equals -x. So y equals -x, we should draw a -1 slope at like 1, -1, 2, -2, 3, -3, 4, -4. Here at 0, 0, so again, weird things going on there. -1, 1, -2, 2, -3, 3, -4, 4. So again, all these make up that line, y equals -x, and along there, I always drew a slope of -1. Okay, what about things like this? I should draw slopes of -2 along anything that's -1/2 x. So -1/2 x, that would be things that, like at 2, -1, so I should put sort of a, I want to go back and erase that because I'm not steeper negative slopes and a slope of -2. So something like that. And then at 4, 2, something like that. Then also at 2, -2, 1 here. So something like that. And then at 4, -2, something like that. Okay. So that gives us a lot of sort of points very quickly there. Now, if you're still not completely comfortable, notice we don't really know much of what's going on here or here. Now you could go ahead and fill in some values, right? And to try to fill this in. Again, you're trying to do a graph here, so you want to try to just get as many points as possible. One thing we could just notice from plugging in here, now that we've sort of exhausted as many isoclines as well, we could make further isoclines. We could do slopes of like 1/2 or 3 or something like that if we wanted to. Just for fun, why don't we just try one like that? Why don't we do like slope of 1/2 and -1/2? I guess that would give us things like y equals 2x and y equals -2x. So we could draw those real fast. Might as well do it. It's our big example of this. So along anything that would be along the line y equals 2x, we should draw a slope of 1/2. So that would be at like 1, 2, So that would be sort of a pretty shallow positive slope. And then something at like 2, 4 should have sort of a positive shallow slope. Then also at like 1, -2, so sort of something like that. And then at 2, -4, something like that. Okay. And then we can do the same here. Anything along y equals -2x should be at -1/2 of a slope. So that would give us things like here. It's going to be sort of a shallow downward there. Sort of a shallow downward there. And then sort of a shallow downward there at -2, 4. All right. If you want additional stuff, you can try to plug in some values. One thing we could observe is that when x is 0, regardless of what y is, this right here is going to give us a slope of 0. So whenever x is 0, we can also put in nice little horizontal slopes. Okay. And at this point, you can probably guess sort of what these things are going to look like. Remember that if there are any intersections between the solution curves, the intersections between the solution curves can only occur when y is equal to 0. If y is not equal to 0, then we know that they have unique solutions, meaning that the solution curves are not going to intersect. So notice we're going to have solution curves that sort of look like this. If we start along here, we're going to be following this guy the entire time. We can see that if we were along here, because the slope would be equal to that line, we would just continue through in here. If we had something like in here, you can sort of imagine this is going to sort of come in through here and then sort of come up like that. We're going to have solution curves that look like that. Why do I know that these aren't going to intersect? Well, they're not allowed to intersect because y is not equal to 0 here, so these have to sort of fit in here. We're going to have some things that look similar to that over here. We're going to have some weird looking stuff in here. What happens when we come through here? Well, these are values in here where y is 0. Notice that that would make the slope undefined. So we're getting stuff that looks like that. Same thing down here. We can see that there's places where it goes flat, and then it's got to sort of match to these. Okay. And then finally over here, same thing. Got places where it's sort of following to there. Right on the x-axis, it's going to go vertical, and there we go. So there are what our solution curves look like for this differential equation. Are there some places where we have some non-unique solutions? For sure. Right in here, right, we've got, this line intersecting, but notice that once we move away from that y equals 0, when we're talking about things up here, there are no intersections between these solution curves. We wanted to call attention to one solution curve just for fun. We wanted to say which would be the one that would correspond to y of 2 equals 1. So if we think of y of 2 and 1, that would be this solution curve right here. You would have that initial value. And by our diagram, we can see that that would correspond to this solution curve here. So that green one there, that would correspond solution to y of 2 equals 1, because that was the curve that went through when x was 2 and y is 1 as the initial condition, and then we drew in that piece there. So there we go. So this is a pretty messy example here, and this is why we sort of made the mention that this slope field stuff is very, very powerful if you have access to like a computer or software that can generate these fields for you. But notice that this Isocline method definitely helps speeds things up. Then it was also advantageous to figure out that anywhere where x was 0, we were going to have horizontal slopes. We also sort of made note, I didn't write this down, my apologies there, but when y was 0 and x was anything, then we had undefined. Remember, y prime being 0 would be horizontal slopes, and undefined would be vertical slopes. So we made use of those like in here. And then we have all this craziness that happens in here, because of course that's where you have that y equals 0 and it might not have unique solutions. So there we go. There's a sort of more complicated example of generating a slope field there. All right, let's take a look at one more example, because slope fields are always a little bit tricky of going through and doing this. All right. So we're going to consider one more differential equation, and then after this example, we'll be ready to actually start solving differential equations rather than trying to rely on graphical techniques or just checking if things are solutions. So let's try to take a look at this differential equation, the y squared minus 1 times y prime equals y. And we're going to do a couple things with this. We're going to prove that every IVP of the form y of x0 equals y0, where y0 is not -1 or 1, will have a unique solution. We'll find any equilibrium solutions, and then we'll draw the slope field, and we'll indicate a solution curve that corresponds to y of 0 equals 2. All right, so a lot of different things with this. This guy should be a little bit easier, though, because notice there aren't any x's in this expression, so we can avoid all that isocline stuff. We should be able to generate a lot of the slopes very quickly. All right, so let's start with A. We're going to do this existence and uniqueness theorem for first order diffie-qs again. However, notice that this initially is not in the format of y prime equals f of xy. We're going to need to divide this over first. So we're going to need to consider this as y prime y over y squared minus 1. And if we look at that, now we can see that the f of xy is this y over y squared minus 1. And of course, the partial of f with respect to y, we'll have to use a little quotient rule. Looks like it's y squared minus 1 minus y times 2y over y squared minus 1 squared. Looks like what? Minus y squared minus 1 over y squared minus 1 squared. Yep, well, are there discontinuities in these guys? For sure. When that denominator is 0, there's going to be discontinuities. But of course, the denominator is only 0 at -1 and 1, which are the places we're trying to avoid anyway. So we can say f of xy and the partial of f with respect to y both are continuous when y is not equal to -1 or 1. So any IVP y of x0 equals y0 with y sub 0 not equal to -1, 1 will have unique solution. Check. There we go. So once again, there are some discontinuities, but as long as we're away from those discontinuities, we are guaranteed that we will have unique solutions. What happens at -1 and 1? Well, we don't really know. Could have unique solutions, could have no solutions, could have many solutions. Just can't say. But certainly anywhere where we don't have an initial condition that involves y being -1 or 1, then we are safe in saying that it's going to have a unique solution. Let's go ahead and do these equilibrium solutions as well. Last one didn't have any, but we'll see about this one. Those are form of y equals k. So we can go ahead and plug that in to our differential equation. We can use this form, or we can use the more traditional form where we've actually isolated y prime. So y prime, of course, is going to be 0 if we're talking about constant. So we have k over k squared minus 1 once we plug in. Bring this on over onto this side, and we get 0 equals k. Well, that is what we're looking for. We're looking for y equals k, so we need to know values of k that would work for that, and we have 1. So we have one equilibrium solution, which is y equals 0. So there is one equilibrium solution right at y equals 0, right at the x-axis. Okay, let's put all this stuff together and build ourselves one final slope field here. So if we go on our sort of last page here, what do we know so far? Well, we know IVPs for y of x0 equals y0, y0 not equal to -1, 1. We'll have a unique solution, meaning that provided we're away from where y is -1 or 1, the solution curves cannot intersect each other. And in B, we know we have one equilibrium solution, y equals 0. Now we're ready to actually try to build the slope field. This time we can avoid all that isocline stuff because we can just plug in the y values. The x values aren't going to matter because y prime is just in terms of the y values, y over y squared minus 1. Okay, so we'll go ahead, put on our field there. So there's 1, 2, 1, 2. Okay. So what are maybe some good x, y, or some good y values to choose here? Well, we already know what happens at y equals 0. That's going to be an equilibrium solution, meaning that the slope is always 0. So we know all along here, I'll do this in a different color so we can sort of see, those guys are always just a horizontal slope whenever y is 0. Okay. Notice that if we try to plug in something like 1 or -1, those are going to be undefined. Right? So undefined, undefined. What does that mean in terms of a slope? Well, that generally means a vertical slope. So we know that we have a sort of vertical slope pieces in here. Okay. Might be nice to sort of know what goes on in here, though we can probably guess, but let's try something like 1/2 or -1/2. If you plug in 1/2, looks like you're going to get something like 1/2 over 1/4 minus 1, which is what, 1/2 over -3/4. I'll bring that up. I guess that's like -2/3. It looks like if we have that, we're going to have sort of a negative slope in there. So in here, we're sort of getting pieces that are sort of downward. Okay. And if we did like -1/2, we'd get -1/2 over 1/4 minus 1, which I guess would be -1/2 over -3/4, which would be +2/3. So in here we have sort of positive slopes. Okay. And then I guess it might be nice to know what goes on up here or down here. So I guess we could do like 2 and -2. So at 2, we'd get something like 2 over 4 minus 1, which I guess would be 2/3. So at y equals 2, we get a slope of 2/3. So we also get some slow positive ones there. Okay. And then for -2, shouldn't be hard to see that we get -2 over 4 minus 1, which is -2/3. So we get some negative slopes down here. Okay, so let's think about what we have here. Well, we know that this is going to be an equilibrium solution, so we can sort of fill in this guy here. Can anything cross this equilibrium solution? Well, this equilibrium solution is at y equals 0, which means that it's away from -1 and 1, so things got to be unique. So they can't really cross into there. So it looks like what we're going to have then is we're going to have some pieces that sort of approach in, go vertical, and then sort of follow along like that. So we're going to have some pieces that sort of look like that. Same thing down here. We're going to have some pieces here. Can't actually touch, though. They go vertical there, and then they come back like that. So it looks like what we're basically having is we're having solutions that are basically different parabolas that are stacked on their sides like this, and that fit in underneath that y equals 0, and then also above that y equals 0. We wanted to find one particular one. Let's just go back and see. We wanted to find the one that corresponded to y of 0 equals 2. So that would be this guy that I sort of already sketched here. This guy looks like he goes through there, and we can sort of see that he would follow that sort of picture. So that would be the solution curve that corresponded to the IVP. This is the unique solution to y of 0 equals 2. So there we go. A little bit easier of a slope field here because it was easier to sort of generate, but definitely a little bit more challenging than the very first one we did. Keep in mind again, while there could be some weird stuff that happens at -1 and 1, everywhere else there can be no intersections, which is why we knew that these guys here became asymptotic to this horizontal line in there. All right, so that's going to finish up our section 1.3. In our next video, we'll be moving into section 1.4, which means we'll finally be ready to actually start solving some first-order differential equations.